Hello everyone, welcome to this session. In this session, we will introduce the concepts in optimization. So optimization problem is the first kind of problem in this specialization that you will solve using AI techniques. So now let's see what optimization is. In real world, we often have to find the best plan or design. This happens often in every engineering domain, that you need to find the best plan or best design. So we call them the optimization or search problem. Often we have two kinds of method for this kind of problem. One is a conventional optimization methods, while the other is AI-based heuristics methods. So in many cases, the latter has a stronger optimization ability and is easier to use. And that is what this specialization will focus on. Now let's first see some popular optimization problems. The first one is a TSP, traveling salesman problem. I think maybe you might have heard that before. So there are several cities that the salesman needs to travel to sell the commodities. However, he has many travel routes. He has many travel plans. So for example, he needs to travel to 4 cities. 1, 2, 3, 4, go back to 1. This is one way. Well, he can also go to 1, 3, 4, 2 and go back to 1. That's another way, right? So each of the routes have a different travel distance. The question is that how to select the travel route to minimize the total travel distance? Or in what order should the salesman visit the city in order to minimize the total distance? And this translates to the cost, right? So this is an interesting problem. So now let's formulate it mathematically. To formulate an optimization problem, the first thing needs to understand is what can we control, right? So what is a candidate solution? How can we represent a candidate solution? In this case, it's a tool. So we use a permutation to represent it. So for example, there are 4 cities. 1, 4, 3, 2. So this means what? I start from city 1, then goes to city 4, then city 3, then city 2, then I go back to city 1. Right, so this is a permutation. Let's make it more mathematically. We call for a tour, a permutation, we call it P, right? P equals to P1, P2 to Pn, go back to P1. So this n can be any value, not necessarily to be 4, right? It can be 20 or 100. So, but no matter what this n is, the tour is like this. P1, P2 to Pn, go back to P1. So in this way, when we have this permutation, we can calculate the length of the tour in a general way. So we can see how can we write that? We can see the L, the length P with a P in is a D P1, P2. So these P1, P2 are the indexes. Maybe this is 4, this is 3, right? The P1, P2, the distance between them, distance between P2, P3, the last one, Pn minus 1, Pn, then from Pn to P1, we go back to the first city. So this is a TSP problem, the length of the tour. So let's summarize this problem. So we can see we want to minimize the total distance LP. The control variable is P, right? So P belongs to omega. Omega is the set of all the permutations from 1 to n, right? The best P must be among all the permutations from 1 to n. So we want to find the best one to minimize LP, right? So we can see some key concepts here. First of all, minimize, right? So some optimization problem we want to maximize, right? Because for example, maximize the income, minimize the cost, and minimize and maximize, they can be considered as the same thing. Because if I add a negative sign before the objective function of the maximization problem, that one becomes a minimization problem, right? So LP, we have seen it before. This is an objective function. For this one, if we want to make it small, the smaller the better, we call it cost function. The P is about the decision variables. P, omega is a search space. We can see these concepts: objective, decision variables, search space. Right. Okay. So how this problem is useful for you? So now I provide you with an application, right? The application is a robot control. So consider you are controlling a robot arm, and you want to draw the holes on the board. So these are the holes, right? So the question is that which order should the robot arm to be used to minimize the drilling time? So clearly this when the robot arm have the smallest drilling distance and then go back to the starting one, then we have the minimum drilling time. So this in fact is a TSP problem, right? So for example, if you are an embedded system engineer, you can build an embedded system containing the optimization algorithm. So that is a TSP. So now we can introduce another popular optimization problem, the quadratic assignment problem, QAP. So this is often used in the city planning. So we can see assign n departments to n sites. We have departments, we have sites. Sites are locations. Departments are the, for example, hospital, right? Factory, this kind of things. So we give the distance between the sites, and in between departments, there are material flow. So we want to minimize the cost of transporting. So how to calculate the transporting? We can calculate it as a material flow multiplied by distance, and we sum them together. So let me give you an example. We have 3 sites, 3 places. Now I hope to put 3 departments into these 3 places. So maybe this is a factory, this is a hospital, and this is a residence, something like that. So now in this plan, what I do is that I put the department 2 into site 3, right? So department 1 goes to site 2. So this is the plan. So after we allocate the department to the site, the material flow and the distance will match each other, and we can calculate the sum of them. So for this problem, what is the question? Department 1 to 3 should go to which sites? In that way, we can minimize the total cost of transporting. Again, let's formulate this problem. First of all, let's see we have distance between the sites and we have material flow between the departments. Now, what is the candidate solution? How to represent it? Same as a traveling salesman, right? So this is still a permutation. So we call it P1 to Pn. In this case, there are 3 of them. So we can say, in this case, 2, 3, 1. We do it like that. So Pi means what? This 1, 2, 3 means department 1, department 2, department 3. So P1 means the site that department 1 goes to. P2 means the site department 2 goes to. So in this way, we can calculate the cost, right? We first use the material flow between the departments, F1, 2. So this is the material flow between the department 1 and 2. Then we make the distance of the site department 1 goes to, the site department 2 goes to. So we can see, and we can do the same as the other ones, and we can sum them together. So this one we can see, calculate the cost, right? So now then we need to make it more mathematically. So how to write the formula like the TSP problem? So here is the answer, right? So after the session, you can expand this and to see if this one is in line with this or not, right? Okay. So these 2 problems, we have a common character. So what is the character? The set of feasible solutions is discrete, not continuous, discrete, and they are natural numbers. Or it can be reduced to a discrete set. So for example, both of them are permutations, right? So finding the best plan, in this case, we call this kind of problem combinatorial optimization problem. Is an important concept in optimization. Okay, so then that's all for this session. Thank you very much. Bye-bye.